from the Indian Women in Mathematics. We have Professor Cheryl Praeger with us today. But before I introduce Cheryl, I wanted to say a few things. The first is that I'm going to request everyone to mute their audio as well as video during the talk. And if while Cheryl is speaking, if you have any doubts,
Excuse me, you are mute. You are muted.
I think when the host muted everybody, I also got muted.
Yes.
I was just saying that everyone keeps their audio and video on mute. If there are any doubts during Cheryl's talk that they want sorted out in a sort of immediate sense, they can just put the question into the chat box and I will place it to Cheryl to answer there and then. But if it is not a question related immediately to the talk itself, then I would suggest that you keep it for the end, because we will have a question and answer session related to the talk soon after the talk finishes. And once we deal with those questions, we will also have a larger interaction with Cheryl and maybe get to know more about her experiences as a woman doing mathematics, and also the various things that she's been involved in Australia to promote mathematics and to promote mathematics amongst women. So these are things that we have planned, and I hope you will have all of us will have a very nice, fruitful, I hope an hour and a half to 2 hours with Cheryl. I also wanted to say, I'm Geeta Venkatraman, by the way, from Ambedkar University, Delhi, and I'm part of the executive committee of the Indian Women in Mathematics. And just 2 lines about IWM before I have the pleasure of introducing Cheryl. So IWM itself has existed now for formally for less than 10 years, but informally for more than 10 years. Um, there were many events which kind of led to the formation of IWM. Once it formally started, it did several activities for the first couple of years, including annual conferences. And then in 2016, and it's always been funded by the National Board of Higher Mathematics, Department of Atomic Energy, Government of India. And uh, once in 2016, basically it was the formatting was kind of reformatted, or a new kickstart was given, and an executive committee was formed with Professor Riddhi Shah from JNU as the chairperson. And now we are in the second phase after that restart. And we have Professor Neela Natraj from um, IIT Bombay, who's our chairperson. And because of the COVID pandemic, many of our activities which used to happen in a physical way could not take place, including our previous annual conference. We hope that we'll come back to you either in a physical mode or in a virtual mode a little later. But please go to the IWM website and you will get an idea of all the different activities that we do. We get supported by the Committee for Women in Mathematics of the International Maths Union as well. We've been supported by them as well. And so with that, it's now my pleasure to introduce Cheryl Praeger. Cheryl actually, in a sense, needs no introduction, especially to group theorists who would have read her papers and, paid a lot of eager attention to the wonderful research that she does. But I wanted to say 2 things about her. She's very recently won the Medal for Science from the President of Australia. And this, I think in the last 20 years, it had not been given to anybody from pure mathematics, and Cheryl has therefore broken new grounds there. And Cheryl's a fellow of the Australian Academy of Sciences. Actually, she has a huge string of honors. That if you go to the Wikipedia page, that if you just type Cheryl Praeger, you will find out a lot of information about her. But one thing which is not there, and I hope she will say something about this later after her talk, is that she had a little role in Akshay Venkatesh's mathematical development. And you may all recall that Akshay Venkatesh won the Fields Medal recently. And Cheryl has a very interesting story related to Akshay. Maybe she will tell us about that after her talk. And I will ask Cheryl to start her talk now. She's going to talk on measuring symmetry with finite groups. Thanks, everyone.
Thank you, Geeta, and hello to everybody in India. I'm so pleased that you invited me to give this talk, and you've chosen this topic. I offered a couple of them. I don't know a whole lot about India. Maybe I'll get another chance to explore and find out more in the future. I've been twice to India. The first time was in 2010 for the International Congress of Mathematicians in Hyderabad and the General Assembly in Bangalore. And then I had another very short visit in 2015 for a meeting at the Indian National Science Academy, INSA, in New Delhi. Actually, I'm really excited that India is doing something very, very special for women in science with its first woman president of INSA now, Professor Chandrima Shah. She's a wonderful woman. I work with Chandrima on a committee for women in science and engineering for the international, a regional Asian network of science academies. But I do have connections with Geeta and another student, Meenakshi. Whoops. My screen sharing.
Please sharing your screen. It has removed Cheryl's.
Someone else is sharing the screen.
By mistake, I think.
Yes.
Pooja, can you just sort this out quickly?
Oh dear.
Sorry about this. These are the disadvantages of online. Yeah,
I'll try again.
We'll try again. Yes.
It's Saroj's screen, so you can ask her.
Saroj, I think
can you see now?
Yeah,
is
yeah,
it okay?
Yep, it's back again. So Meenakshi and Geeta were my friends, and I have a colleague, Neela, now. We work together on the Committee for Women in Mathematics of the IMU, and I guess we'll be having a Zoom meeting of that committee in about a week's time. Anyway, let's go on to this lecture. There's that picture. That's the only picture I've got of the General Assembly in Bangalore in 2010. Okay, so I am absolutely passionate about symmetry. And symmetry means what you think it means. In nature, it seems to symbolize beauty and health. And there's wonderful examples like this one. But it also is very, very important for very much of science. In fact, Nobel laureate P.W. Anderson says it's only slightly overstating the case to say that physics is the study of symmetry. And it's one of these really critical concepts that underpins a mathematical understanding of the world. And as well as physics, it's important in the theory of networks and information technology that we are depending on these days with our electronic communications. So mathematics describes symmetry using abstract structures called groups. And these groups, they help embody concepts like repetition of patterns, like this frieze group at the bottom here where the pattern gets repeated as we move along. Reversibility of motions, like moving between different types of solids and liquids and gases in chemistry. And if we put all of these symmetries together, they form these groups, and that groups can give us a sort of a complete understanding of various families of objects. In this particular case that I drawn a picture of, to do with freezers, you can use the theory of groups to explain that there are exactly no more and no less than 7 different types of freezers. Because symmetry really imposes quite amazing restrictions on structure, which really helps us understand the world. So what is a group? Well, if we put all of the symmetries together of a structure, we will get its group of symmetries. And here's a very simple example, is the group of all the rotations and reflections of a circle. So we can rotate through the center by any angle whatsoever. We can reflect the circle through any axis through the center. So this is a very huge group. It's an infinite group. And some groups may be finite, and we'll be talking about those later. Group theory emerged almost 200 years ago, and it came through at least three different routes, because it was a very natural set of ways of thinking. So it came first through study of polynomial equations, looking at the symmetries of their equations. The group of permutations of the symmetries led to the work of Galois in 1830, and probably before that. It also came through the groups related to geometry, symmetries of geometrical configurations, and that came up through Klein a little bit later in the 19th century. And again, it came through number theory, where we hear a lot about number theory from the mathematics in India. The factorizations into prime numbers and the symmetries associated with that came through the work of Kronecker in 1850. So there are 3 different routes of groups, and finite groups, as well as those infinite groups I looked at, are pretty important. You'll see them in biology, and I've got a bit of a diagram here of a capsid depicting the structure of a small virus, where there are 60 degrees of symmetry with what we call icosahedral symmetry. And you'll also find symmetry in architecture, and both the viral capsid and in architecture, they're sometimes built up of very small components which are repeated and repeated using the symmetry of the structure. So that in biology, you just need this small amount of biological information together with the symmetry to help the virus replicate, unfortunately. Anyway, let's move on to the theory. Finite groups are actually formed themselves from small components that we call simple groups, and we chop up the finite groups into finding these simple groups. And sometimes we call the simple groups the composition factors of the group. And I want to show you a picture where I was trying to explain to some government scientists in September last year. They were making a video to show when I was, when my Prime Minister's Prize for Science was announced in October. They wanted to show in a pictorial way what it was I did. And so I was explaining that we can start with a group and we can chop it up. Group theorists would say we had a normal subgroup and a quotient group. We chop it into 2 smaller groups. And each of those we might chop again into, again, 2 smaller groups. And as the groups are getting smaller, we can't go on forever. And we get to a point where we can't chop anymore. And so when we get to that point, we've got a simple group. And so we depict this as a tree. And the simple groups associated with the group we started with are all the leaves of the tree. They're the composition factors of the group. And you can tell a whole lot, not everything, but a lot about the group from the simple groups, which are its composition factors. For example, you might have many different composition trees, but you will always get the same number of simple groups of each type. And you can multiply the sizes together and you'll get the size of the original group. So what are some groups that we know quite well? Well, one of the groups is the clock group, and I have this picture that was developed by a wonderful mathematician called Robin Whitty, who makes pictures of mathematics called the Theorem of the Day. And this is one of the theorems of the day about one of my theorems. And he talked about the clock group where he was taking 24 hours, but perhaps to fit in Indian time zones and my time zones, we should have think of 48 half hours. But if we go back to 24 hours, what the simple groups that make up this cyclic clock group are a cyclic group of size 2. We get 3 of those, and one of size 3. And if we multiply 2 times 2 times 2 times 3, we'll get the size of the full group, 24. And so we actually get these cyclic simple groups, cyclic of prime order, one for each of the primes P. And that's like one infinite class of simple groups. But there are other simple groups which are not as nice as those cyclic groups, or not as easy. Most of the other finite simple groups come in infinite families, and most of them are called infinite families of Lie-type groups, and that was named after a Norwegian mathematician from the 19th century, Sophus Lie. And most of the Lie-type groups, most of the non-cyclic simple groups were actually known by mathematicians by the 1960s. We didn't know that there weren't any more, but as it turns out, all of these infinite families were known by the 1960s. And as well as them, there are 26 other simple groups. The largest of them is called the monster, and that's how big it is. That's the number of its elements. And it was constructed in 1979. And so the classification of the finite simple groups is now complete, and it was nearly complete by 1980. It took just a little while longer, till about 2004, to really pin down all the details of the proof. And the first proof that says we know all the finite simple groups takes about 10,000 journal pages. And you can talk about these simple groups a bit like the periodic table of elements in chemistry. And an American PhD student, Ivan Andrews, in 2012, decided he would draw a picture of the finite simple groups to explain to his father what they were like. And so he drew this very lovely diagram of all the non-abelian simple groups. There's a column on the right-hand side, which are all the cyclic ones. These are one for every prime order, C2, C3, C5. So that's supposed to represent an infinite family of cyclic groups. And then these other columns, most of them represent the infinite families of Lie-type groups. On the left-hand side, there are what's called the infinite family of alternating groups. And the top one should be representing the group of the capsid of the virus. And then the 26 sporadic groups, they don't fit into infinite families, and Ivan drew them down the bottom. Now, this classification of finite simple groups has been called one of the greatest achievements of 20th century mathematics. And that's taken from the citation for the 2008 Abel Prize, which was awarded jointly to John Thompson and Jacques Tietz, two of the giants who had a lot to do with the classification of the finite simple groups. And we think of them as the atoms of symmetry. And they're what I want to talk about in the mathematical part of today's talk. So for a general finite group, I've explained that it gets made up of a collection of finite simple groups, its composition factors. And the number of those composition factors, that's the number of the leaves on this tree, we'll call its composition length. And there might be many composition trees, but the composition length is always the same. And so that's what I'm going to talk about. It's the number of composition factors when we count each according to the number of times it occurs. So it's the number of simple groups involved in the group. And for the clock group, we had 3 C2s and 1 C3. So its composition length was 4. 3 plus 1 is 4. So I'm going to talk about ways of estimating or bounding the composition length in terms of things we care about. So composition length of a group. It's one way of measuring how complex the group is. Of course, every simple group has composition length 1, and some of the simple groups are not all that simple, but we're just going to count the number of simple groups. So we've got the composition length. There are other measures of how complex a group is. And of course, one is the size of the group. Well, that can be much bigger than the composition length, right? Another is the smallest number of elements of the group you would need so that you could generate all of the elements of the group by just repeatedly multiplying them all together in some ways. And that's called D of G, the minimum size of the generating set for G. And these are all kind of related. Like the minimum size of the generating set is at most twice the composition length. The composition length is at most log of the order. And so I'm just going to be talking about the composition length today. It's most useful if I tell you something about the composition length in terms of the way I'm thinking about the group, I'm working with it. So it might be that I have a group of permutations of a set of size n. Then I would like to know how big is the composition length relative to n. Or I might have n by n matrices over some finite field of size q. I might want to know how big is the composition length related to n and q. And these are the two types of ways in which groups are most often studied on computers and very often studied by people studying symmetric structures. So I'll say it again, a permutation group. Well, this is a group, subgroup of permutations of a set of size n. And the symmetric group is the name given to the group consisting of all the permutations of x. So if I had x consisting of the numbers 1, 2, 3, then there are 6 permutations and they make up the symmetric group Sim3, and G, a permutation group, there might be some or all of those permutations forming a group. The second type of groups we're going to look at are the linear groups, the groups of matrices, groups of invertible n by n matrices. I want them to be finite, so the entries will come from a field of...
Cheryl, sorry,
yes.
I'm just going to quickly interrupt you and ask you a question which came up on your
Yes.
previous slide.
Yes.
Kapil Paranjpe asks that to say that D of G is less than or equal to 2C of G, one needs to know that simple groups are 2 generated. Is there a simple proof of that?
There's no no simple proof of that without using the classification.
Okay. sorry to interrupt.
Yeah, that's a very, very good, smart question. Yes, I should have said that, but well, no, I shouldn't have said it, but thank you for the question. So the general linear groups, if we take the tiniest one, so to take 2 by 2 matrices and a field consisting of just 0 and 1, well, then we again get just 6 invertible matrices. And in fact, this group, GL22, and this Sim3 group, theoretically, they are what we call isomorphic. They're just a different way of labeling the elements of the same group, so that you can represent the same group in different ways, just depending on what is most convenient for the sort of work you're doing. Okay, that's the context that we're going to look at. So if I'm going to talk about permutation groups, one of the properties I will be interested in is whether the group is transitive. That means whether for every pair of points, alpha and beta, I can find a permutation in my group that takes alpha to beta. If I can do that always, then we say the group is transitive. And we divide up the transitive groups into the primitive and the imprimitive ones. Now let me try to explain what I mean by these. So being imprimitive, it's funny that it's got the negative word here. Being imprimitive means that the group preserves a non-trivial partition of the point set. Here is my favorite example. If I take the points, the 4 points, which are the corners of the square, and I take the group to be the group of all rotations and reflections of the square, then the opposite vertices get mapped. Pairs of opposites go to pairs of opposites. So rotations might swap pairs, two different opposite pairs or antipodal pairs, or they might leave them alone. But this partition into opposite pairs is preserved, and that group is therefore called imprimitive. The group is primitive if the only invariant partitions are trivial ones. That means really the partition just had all the parts in one, all the points in one part, or all the parts had size 1. And we think of the primitive groups as the building blocks for permutation groups. All the transitive groups can, in a sense, be built out of primitive ones. Okay, so that's what we're going to study. And they're the concepts we need to know about. What about linear groups? Well, the sort of properties we care about here is whether we can write the underlying vector space, which will be an n-dimensional space over a field of size q, whether we can write that space as a direct sum of smaller subspaces such that each of those subspaces is invariant, that is mapped to itself by the group G, and is irreducible in the sense that we can't split it up any further. Now here is a tiny example. We might have the vector space written as U plus W, and U might be the span of the first few basis vectors and W the span of the rest. And then the group G might consist of all the block matrices with matrices permuting U in the first block and matrices B acting on W in the second block. And so this would be an example of a completely reducible group, which is not irreducible. So they're the sorts of linear groups we'll be looking at. And they're kind of the ones which are useful by people working with representation theory of groups. Okay, so getting back to composition factors. Quite a lot was known about the composition length of permutation groups. Way back in 1974, which is quite a long time ago, isn't it? 30, 40 years, yeah. Lovely paper published by a man called Fisher. And he said, if you have a permutation group on n points, now he doesn't care what that group is. It could be transitive or not transitive, primitive or not primitive. He says always the composition length is at most about 4n over 3. And he made it just a little bit finer. He said if this group has got s orbits, then the composition length is at most 4n minus s divided by 3. And in his paper, he showed that you couldn't do any better than this. And he gave an example of a group, and I'm not really going to say what this is, but if you know about it, it's some sort of iterated brief product. it's a permutation group that is transitive on 4 to the k points, and it has composition length actually 4 times n-1/3. And we'll come back to that in a bit. So that is what happens for general permutation groups. There's another paper published 20 years after this one by Lotzi Praeger, Hungarian mathematician, and he states that if you don't look at arbitrary permutation groups and you look at primitive ones, which are not just symmetric or alternating groups, then he says, because these are the ones he's interested in, the composition length is at most a constant times log n. So it's jumping from a constant times n to a constant times log n. And then for completely reducible groups, another 8 years later, there's a paper by Lucchini and Menegazzo Morighi, some Italian mathematicians. They go for completely reducible matrix groups, and they get an upper bound, which is a constant times dimension n times the log of the field size. Now, why have I put states here? Praeger never proved this result. He just stated it. And Lucchini and those people, they used Praeger's result to prove theirs. So these constants are not exactly the same constant, but this one exists because they used Praeger's result. And in fact, it turned out that Praeger did eventually publish about a proof of this result in a paper published in a journal that's dated April 2017, but I don't think it came out until quite late in 2017 by Guralnik, Marotti and Praeger. And he says, this is true, and we can take this constant, horrible looking one, but it's about 4.25. So it's not a huge constant, it's quite small. But just remember that number, 4.2 something. Okay, so where do I come into this? I have a colleague called Stephen Glasby, and in February 2017, so that's before we knew about the Praeger's results, Stephen was saying, well, we have Fisher's bound, and we know it's sharp. It's certainly sharp for transitive permutation groups. We have Praeger's stated bounds, but we don't know what this constant is, and in fact, Praeger hadn't published a proof of it. We have these this paper about matrix groups, and we don't know if that's sharp either. Is it possible to find sharp upper bounds for primitive groups in Praeger's case, or for linear groups? Can we find sharp upper bounds? And if we can, could we classify all the groups which attain those bounds? So that was his question. So just reminding you that I've already told you this, haven't I? We want sharp upper bounds for the composition length for primitive permutation groups, and the primitive ones are the ones which don't leave invariant any partitions. Cool. So here are the people. This is what happened. February 2017, my research group had a research retreat. This is in the summer, so it's very hot. And here's everyone on the research retreat. We would propose problems and then we would work together. And it turns out that 4 people ended up working on Stephen's problem. This is Stephen Glasby. This is Kyle, who was a master's student at the time. Here's Gabriel Verret. Gabriel's from Auckland. He'd come across for the research retreat, and here's me. And so we're the ones which ended up working on this problem, our work started off at our retreat at Moondine Retreat in the Avon Valley, back of Perth. So Stephen said, okay, let's look at Fisher's groups. What are they like? Let's consider the extreme cases. Now, the first one of Fisher's group was actually this symmetric group, the group of all permutations on 4 points. and it's got size 24. It's the same size as the clock group, and it's got the same types of composition factors, 3 C2s and 1 C3. So its composition length is 4. It's nothing at all like the clock group, but it's just got the same composition factors. And we're thinking of it acting on a set N1 of size 4. And according to Fisher, the composition length is at most 4/3 of number of points 4 minus number of orbits 1, which is true. 4 times 3 over 3 is 4. Okay, second group is this really strange one. Now it's an imprimitive group. It's going to act on a set of size 16. That's 4 copies of the first set of size 4. And on this set, I'm going to put one symmetric group on 4 points on each of these 4 blocks of size 4, and another sim4 permuting the 4 blocks. So I've actually got 5 copies of sim4 making up this group. And each of the sim4s has 4 composition factors. So altogether, I've got 4 times 5 is 20 factors. And that equals 4/3 of number of points 16 minus 1. So it works. So how do we get all of them? Well, if we got the k minus first one, the way we get the next one, the kth one, is we take a whole lot of sets of size 4. And the number of sets of size 4 is the number of points that the previous group acted on. So the new set size is 4 times the old size. So it's going to be 4 to the k. And the number of composition factors is that we get 4 to the k minus 1 times 5, because we've put, 4 to the k minus 1 times 4, these ones that we put on here, plus the old number that we had available. And we work it all out and it works. So we've got this way of understanding what Fisher's groups look like, and we can do our sums and we can see that the numbers work out. Now, it turns out that these same groups, Stephen understood, could act in a different way. They could act primitively. So the first one, it just acts in the same way. Set of size 4, and we know this, Stephen's called them P1. I'm using his notation, P1 for primitive one. It's got 4 composition factors. The second group, well, it's sim4 is sim4. We know it's got 20 composition factors, but Stephen's made it act on a set which is actually 4 tuples from a set of size 4. So the size of this set is 4 to the 4. And the third group, well, again, it's sim4 with the previous one, and it's acting on a set of 16 tuples from a set of size 4. So he constructs these new actions of the old groups so that the set sizes are different numbers. So the set size is actually 4 to the 4 to the k. And when he does the sums, so we know the composition factors, we know that it's 4/3 of 4 to the k minus 1, yep. But in terms of the number of points we're permuting, this is actually logarithmic. So 4 to the k is like log to base 4 of n. So his composition factor worked out to be, when he did the sums very in great detail, 8/3 of log to base 2 of n. And Stephen thought, maybe that's as good as it gets. Maybe this is the largest composition length you can possibly get for a primitive group on n points. So that's what his guess was. Now let me tell you what we proved, because it was really rather nice. So let's go through what did we manage to prove about permutation groups. Well, here's what Fisher had. the composition length is about 4/3 of n minus s, where s is the number of orbits. Now, our contribution here was to say that, yes, Fisher knows that equality can hold, but we proved that equality holds if and only if the group is a... Can I keep going?
Aritra Roy, please mute yourself.
So equality holds if and only if the group is a direct product of one of these little Fisher groups. So you know exactly what the extreme examples look like. We actually needed to know this for our later work. And the proof, well, it's just an induction proof on the degree. It's quite pleasant. You can read it quite nicely and reduce down to a primitive group. We use a little bit of computation for small values because it was convenient. But then, because we were going to use the finite simple group classification later, I have to confess that we used a result of Morotti, which depends on the classification, about the orders of primitive permutation groups. Maybe there's an elementary proof, but we haven't actually put that in yet. So that's our proof for general permutation groups. What about primitive groups? Well, we actually proved Stephen's guess. We proved that the composition length of a primitive group on endpoints is at most 8/3 times log n. And we put in this extra little bit because then we could show that equality could hold, that this was the best possible group you could get. So equality holds if and only if n is one of these powers of 4 and the group G is one of these primitive groups that I told you about a few slides back in product action. So what this meant was that, yes, the best possible p-bear constant C is going to be 8/3. Now, in fact, 8/3 is what, 2.666, yeah? It's way less than what p-bear was showing in his published paper in 2017. So although we didn't even know that he was going to publish that paper, at least we've got something nice to offer. We can say this is the best constant, and these are the groups for which it has been achieved. The proof was much more complicated. We used what's called the Onan-Scott theorem, which is a natural thing to use in primitive permutation group theory. But there's one particular type of primitive group called the affine groups, which are they're groups of affine transformations of vector spaces. And for that sort of group, we actually needed to prove a theorem about matrix groups to slot into our proof about this theorem for permutation groups. So let me tell you what our theorem was about matrix groups. So what we had to prove was that for completely reducible linear groups, these are these ones where they'll split up the space into a direct sum of invariant subspaces, that the composition length, so it's n by n matrices, field size Q, the composition length is less than 8/3 of n log Q. So again, this 8/3 is coming up as the best constant. We wrote it out in a very yucky way. So if you have a look here and you're used to taking logs, log to base 2 of p times f is log to the q. So we've got a rather complicated expression here, and it's technical, and the only reason I've written it out is to tell you that we needed this technical expression to use in an inductive proof. So we proved that the composition length is less than this, and that this little inequality here can hold, and it holds if and only if the prime p is 2, and the groups are products of things which look a bit like a matrix group version of the Fisher groups that I was just talking about before. So we kind of know what the bound is, and what the most extreme examples are. Oh, so here we are. General groups. Fisher says composition length is at most 4/3 is less than 4/3 n. Primitive groups less than 8/3 log n. So what's the difference between general groups and primitive groups? Is there some kind of boundary where you get a linear bound and then somehow or other a log bound? Are there some other classes of groups where you can get a logarithmic bound? Well, yes, there are some. There's some other groups called quasiprimitive groups, which are a larger class of groups than the primitive ones. Technically, it means every non-trivial normal subgroup is transitive. These ones arise pretty naturally in studying graph symmetry. They give you a logarithmic upper bound. There's an even larger class called semi-primitive ones, where a natural example is the general linear group acting on non-zero vectors. They give you a logarithmic upper bound. But, well, what have we got here? We, let me see, for the, yes, I decided to cut out a whole lot. But I have to confess to you that we don't really yet know what is the natural class of groups which tell you, yes, here we have a logarithmic bound, and somewhere else, if you relax it a bit more, you're going to have to go into a linear upper bound. So as a result summary, for completely reducible groups, we have got sharp upper bounds in terms of n and the field size. For primitive groups, we have, again, sharp upper bounds, and we classify all the examples attaining those bounds. We've got logarithmic bounds for some other classes of groups. We cannot get the best constant yet for quasiprimitive groups. That's an open question. And we do not really know what is a nice borderline between the log and the linear upper bound. So that's where I would like to say thank you for listening, and I'll be very, very happy to answer any questions you might have. So thank you from spring in Western Australia. Here's a couple of our spring flowers that my husband took pictures of in the last few weeks.
Thank you, Cheryl. There are two questions already. One had come up during the time when you showed the composition tree.
Shall I go back to that?
Yes. So Jasina Hamid PK asks, ma'am, she wants to know whether the composition tree of a group is an example of fractal geometry.
That is a rather pretty question, isn't it? I've been looking at composition trees of finite groups. So although we might get something approximating a fractal, it wouldn't really be a fractal.
She wants to know whether the composition tree of a group is an example of fractal geometry.
Yes, well, we wouldn't really get fractals, because fractals you can zoom in and make things smaller and smaller and smaller. But for a finite group, we're always going to get a finite number of leaves. So it wouldn't quite look like that. You could get something a bit like it if there was an approximation for infinite groups, but not every infinite group would give you a composition tree, because you might not be able to, let's see, I don't know. I actually don't know what the answer would be. I'm sure there must be some families of infinite groups where you would get some dynamical system which would be constructing a composition tree that might look like a fractal, but I don't know the answers there.
The suggestion from Suri is maybe a p-adic group could give a fractal. P-adic
Maybe, yes. As long as you can keep going. in a sensible, well-defined way to sort of allow you to construct the tree.
There's another question from Suri. He wants to know, does the classification of finite simple groups show that finite simple non-abelian groups are 1.5 generated? Meaning, can one generator be chosen arbitrarily?
That is a theorem that's either proved or almost proved. I was listening to some lectures about it, and I'm not completely up with the most. So I should explain what we mean by 1.5 generated. So for the group to be 1.5 generated, you give me one element and you can choose it, and I have to find another element that will, so that those two will generate the whole group. Is that right? Are we understanding the same concept?
I think so. Yes. He says yes.
Yes. And I think that is just about a theorem. I'm not up with all the papers, and I think that many of my colleagues are looking at even finer questions where perhaps we might be given 2 conjugacy classes and you want to specify that your second element should be out of the second class or something. So that there's many questions which are being asked about the finite simple groups.
There's a question from Ved Prakash. He asks, do people consider the lattice of all subgroups, not only simple subgroups of a finite group, and study it as an abstract lattice?
Yes. Well, mathematicians are always studying the lattice, in particular the lattice of subgroups of simple groups, because we need to work with simple groups. But you're asking about whether we study it as a lattice. There's some very, very interesting work of Ashbacher and others about whether certain small lattices can actually occur as sublattices of a group lattice. I mean, there are some very interesting questions which are related to the lattice as a structure.
There's another question from Lavanya. In the composition tree, can the composition tree be related to graphs?
What am I going the wrong way around? Can it be related to graphs? Almost anything can be related to graphs. Certainly generation can be. There's lots of wonderful theorems being proved about the graph telling you when 2 elements are going to generate a simple group. The pairs, that sort of graph is called, I think, the Saxel graph, after my colleague Jan Saxel, who died recently. But can the composition tree be related to a graph? Well, we've drawn it as a graph, as a tree, but perhaps you're thinking of some other more pretty interpretation.
There's another question related to graphs from Neelam. She asks whether you can relate the composition tree structure with prime graphs of groups.
I think the answer there's probably not naturally, Neela, because the composition tree isn't that fine. So the prime graph of a group, its nodes, its vertices are elements of the group, or sometimes conjugacy classes, whereas here the nodes are subgroups. And it's probably not such a natural linkage. But there are many, many graphs that people work on to get insights into groups. The prime graph, where you take the prime divisors of the order of the group, they're your nodes in your group, and then you join them if there's an element. So there's always an element of each prime order, but you join them if there's an element whose order is the product of those two primes.
Yes.
And then there's other graphs where you look at primes which divide the conjugacy class sizes, and you join. You have two sorts of vertices, primes and conjugacy class sizes, and you join them if the prime divides the size of the conjugacy class. Or you might have primes and irreducible character degrees, and you join them for the same reason. And these graphs are, in a very subtle way, related and very interesting, and people are, my colleagues are finding more and more out about this structure. So the graph structure tells you something about the group structure.
There's a question from Siddharth Sarkar. Is CG, does it have sharp CG? Is it sharper? Are there sharper bounds for sharply 3 or 4 transitive groups?
Well, yes, I understand. I'm just trying to think where to put this. So the sharp bounds for the bound that I showed you, it's the exact the groups achieving the bounds are a long way from being 2 transitive or 3 transitive or 4 transitive. I mean, they're a long way from that. And so one of the results that we proved, that I took out of this slideshow because I thought it was too technical, is that all of these extreme examples are what are called affine groups. And if we don't want to look at affine groups, then we can get an upper bound which has a smaller constant here. So there are many, many interesting questions, and we've only looked at some of them.
But the logarithmic part would still remain the same.
Oh yes, the logarithmic part is still there. We're only winning by changing the constant in that case for looking at primitive groups. But I mean, if you're asking about, say, 2 transitive groups, the worst case would be the affine case, because you could take n to be a power of 2, and the affine group would have an elementary abelian subgroup of order n, so it would have log n factors. So you can't get better than log n in that case. And if you had n being a power of the prime p, you would get log to base p of n factors just from the translation group. And we can get 2 transitive affine groups. So we can't remove the log in that case.
Right.
But if you go away from affine groups, maybe you can.
Riddhi Shah wants you to say something in general about the classification of finite simple groups. What's the general impression of the result, and so on?
You mean, do I believe it? Yes, I believe it.
But it's still something that, if a proof uses classification of finite simple groups, I mean, it's sort of
it's using a very
flag.
yes, it's using a very deep theorem. So I don't believe that you could prove any of these results without it. So there's something general. Whenever a mathematician uses the classification of finite simple groups in a proof, we should say that we're doing it. And we should only really use it if there's not an elementary proof. And as long as we say that we're using it, then if somehow the classification missed a group or two, as long as it's clear where it's been used, then all those results can be checked. On the other hand, if we keep using the classification, especially as I have done, to justify some randomized algorithms for computing with groups, if we're using those algorithms and the algorithms themselves rely on the finite simple group classification, then maybe we would never find a new finite simple group if perhaps the classification were wrong and there was one existing that we hadn't discovered yet. There are many things you can say about the classification. It's the most wonderful, powerful tool to help us study symmetrical structures of all kinds.
Yeah. So two other questions connected to classification. One is that whether the 10K page proof takes the help at all of computers. And the second is whether the odd order theorem is used in the classification of finite simple groups.
Yes, definitely yes to the second one, because the way the original proof went up that 10,000 page paper or collection of papers and the revised group, they're all relying on looking at what's called centralizers of involutions, elements of order 2. And you'll only know that a non-abelian simple group will contain an element of order 2 if you use the odd order theorem that says all groups of finite groups of odd order are soluble. So yes, I believe that it is used in every proof up to this point and probably in the future. And were computers used in the classification? They were certainly used to construct some of the sporadic simple groups. So theoretically, for example, in perhaps the earliest anecdote I know is Yanko's first simple group discovered in the early 70s, 69, early 70s. He worked out theoretically how big it should be, that it should be represented by 7x7 matrices and over a certain field. But then to prove that it existed, that relied on a very, very, very clever computational construction by some mathematicians at the ANU and in Melbourne, I think, just to prove that it existed. So you could prove that it ought to exist and it ought to have all these properties, but to prove that it existed, you needed someone to construct you the matrices and then somehow or other check that those matrices generated the group of the right order. And that was done with a computer. And so computers have been used in that context in other parts of the classification as well.
There's a question about whether finite groups arise as automorphism groups of graphs. This is from Isha. Answer is yes.
Oh, do you mean whether every finite group arises as the full automorphism group of a graph, or I mean that
you can answer both.
Well, let me say that graph theoretic methods are extremely important in studying permutation groups, and those methods were developed in the 60s and 70s firstly by Donald Higman, Peter Cameron, and they automatically start with a group and build a whole family of graphs out of it. And the group is acting as groups of automorphisms of those graphs. And they're very useful and a very visual way of working with groups. On the other hand, if you start with graphs, you can learn a lot about families of graphs by looking at their automorphism groups as well. I've done that a lot.
There's a question from Navpreet Singh. He asks, whether in your proofs, do you find a use for categorical concepts?
Ah, I used to love category theory. I thought I was going to be a category theorist before I went to Oxford to study for my DPhil. I don't use them very often, but they are very important in studying certain parts of representation theory for groups and in studying more geometrical objects. So I personally don't use them in what I do, but in other areas of group theory, they are very important.
One more question from Bharat Talwar. Log 2 tells us how many 2's divide the order of a group. Should not log p for different primes p be helpful in achieving better bounds?
Well, it depends how you want to write the proof here. I think the answer's no. It
Yeah.
won't give you better bounds. You could very easily substitute whatever base you wanted to here, but then you would have to put an extra constant out the front. And the reason that there is a 2 here is that the inductive proof was easier, that the 8/3 was more giving us more information. And remember, we've got a less than or equals here. So if we had any other bound, we would go less than or equals that whatever the constant was, log to base 2. So this is the worst case you can get, the biggest number that you can get. And the problem is that we need to have the 2 there because the extreme examples are 2 groups.
So there are two people who are responding saying, Kapil is saying that a physicist's answer, smaller the unit, the better the measure. So log 2 is a better measure than log 3. And Suri is also agreeing to that.
It's a matter of taste, isn't it? We could use the natural logs, but then we would have to have some very irrational constant here.
Cheryl, so I think we don't seem to have any more mathematical questions.
Okay.
Would you like to tell us a little bit about your interaction with Akshay? Okay, there's one more question which has come up, which is there a proof of Onan's theorem without using classification of finite simple groups?
Oh, yes, definitely, yes. But it depends what you mean by the Onan-Scott theorem. There's a proof of almost all of it, but I think there is one bit that some people might put in and other people wouldn't, which says that for the almost simple primitive groups, that the unique minimal normal subgroup, that simple group, should not act regularly or something. And so there's just one little bit that might be an extra add-on that would depend on what's called the Schreier conjecture about outer automorphism groups of simple groups being soluble, which is now proved. So essentially the Onan-Scott theorem does not depend on the classification, I would say.
So of course, there's a lot of people who writing in saying they've enjoyed the talk and so on. And but maybe a little bit, Cheryl, if you could say about how you met Akshay and what happened. That's one thing, and the other is how what kind of work you've been doing. I saw that there's a family program in mathematics that you instituted for women, school, girls in school or something.
Girls in school maths, yes.
So maybe think about these two things, and then we'll see if people have questions about your experiences as a woman mathematician and so on. So,
yes. I actually prepared another little presentation, but maybe I'll talk about Akshay first and then show you the pictures. There's a lot of pictures in it.
Right.
Yeah. Okay, so Akshay, what a wonderful, wonderful mathematician. I met Akshay first when he was 11 years old. Yep. His mother came to talk to me about the fact that he couldn't stay in school for too much longer because his teachers couldn't give him the right sort of support. And at some point, Sveta, his mum, she's a computer scientist. She said, I think it's time for you to meet Akshay. And so she brought him in. So maybe he was 12. Perhaps he was 12 by then. And I was head of department. So he was sitting at the table in the head of department's room while I was talking with his mum for a little bit. And I went back and I saw Akshay, and he said, oh, what's all this written on the whiteboard, on the blackboard, or maybe it was. And I said, oh, well, I've just finished a PhD supervision with my student Greg. And he said, well, what's it about? And I said, well, it's about the problem about group theory, about permutation groups. And I explained a little bit more. And he was okay. He sort of knew about groups, and he was really, really surprising, really impressive, even at age of 12. So he came to university age 13, and he did a 4-year undergraduate degree in 3 years. He just overloaded, did many more units. He liked everything. He was doing physics, he was doing mathematics, but he pretty soon decided he wanted to study mathematics. And so for his 4th year, which we call an honours year, where the students do a project, he asked if I would supervise him, which was wonderful for me. And his colleague, Michael Giudice, who's now head of pure maths in my department here, Michael wanted me to supervise him as well. And I hadn't really been expecting to have 2 student projects. And I said, oh, I've only got 1 project. And they said, oh, we'll both do it. I said, no, you can't both do the same project. So they both said to me, all right, you can have the weekend and come up with another one. So I had to think up a second project and bring it up to them, and then they had to choose. So I had an absolutely glorious year supervising 2 extraordinary, wonderful students. So, yes. You can ask me. Was it another story, or was it that one?
Yeah. So no, you had mentioned the story to me, I think, when we met last. So I totally share this with. Also, now your experience. You had pictures to show us.
Yeah, I have. Shall I find them? I don't have to go if they're. How do I do it? Let's see if I can it doesn't let me unshare.
You've lost the pictures.
No, yeah, I have to get out of full screen mode and change which one it was. Yes. And now I can share it. Sorry. And perhaps trying to get into.
I like the title.
Yeah. Yes. So there's a story behind the title. So I'm pretty old. I was born in Australia, in Queensland, and the family, we grew up in different towns. My dad worked in a bank and ended up completing high school in Brisbane. And I didn't know, I didn't know whether I was good enough to do maths at university. And I didn't know that you could study maths, and I didn't know that you could get a job doing mathematics. but I just really wanted to study some more. And I went to a government vocational guidance person who told me, girls don't do maths, they don't pass. And I got so cross. And I had told this story in a a video interview much later. Bernard Neumann, Prof. Neumann was interviewing me. And when I was going to speak at the European Women in Maths Conference in 2009, the organisers found this interview online, and that story struck a note, and they used it as the slogan of the whole conference. Oh no, a woman doing mathematics. And this is the speakers catalogue for the conference. So that was my start to doing mathematics. As I was a student at university, I was in fact the only girl. I was doing advanced honours maths courses all the way through, but from my second year on, I was the only girl in my class. There was one other girl. I was also doing honours physics, advanced physics. There was one other girl in physics in my second year, but after that, I was the only girl. But somehow it didn't feel so so terrible, because I had two women maths lecturers. This is one, Anne Street, and this is the other one, Sheila Williams. And Sheila had been a fellow at St. Hugh's College in Oxford, so she was the one that encouraged me to go to Oxford. And between my third and fourth year, I won a vacation scholarship and did a research project in Canberra with Bernard Neumann as my supervisor. And Bernard's wife, Hannah, was the first woman to be a professor of mathematics at an Australian university. And so I met Hannah in those days. Unfortunately, she died very early. But I knew these women, so it didn't seem such a strange thing to me, even though I had no other girls in my classes. So then I went to Oxford and finished my DPhil, and I went to America for a little bit, back to Canberra as a research fellow, went to the University of Western Australia in Perth, eventually got a continuing job there, and then they advertised a professor's job in mathematics. You couldn't get promoted to professor. You could only be a professor if you applied for a professor's job in those days. So me and 85 other people applied for this job, and I got it. And this is what I looked like. I was 35 years old. The university published an announcement. So I became professor late in 83. In February 84, the university, in their alumni news article, published this picture of me. And they said, a young woman who is involved in research of international significance, Professor Cheryl Praeger, 35, is only the second woman in Australia to attain a chair in this discipline. And so it was quite an unusual thing to be a woman professor of mathematics. So many of the newspapers were interested. And they were really interested in the fact that I had two little kids. So Tim was about, 15 months old, and James was 3.5. And so 3.5? 4.5. So they took lots of photographs of me and the children. We even made it to the front page of the main newspaper in Western Australia. And the title down here, it's cut off a bit. It says, "On a bike built for three." But this is a fake photograph. The real one is there. My husband, John, is in the picture. He just got sliced off for the newspaper. So we had to buy a copy of the real photograph. So there I was. I've done many things, I guess. I was, the first woman to be president of the Australian Mathematical Society in '92. Gave an invited lecture at the International Congress of Mathematicians in Beijing in 2002. I was a fellow of the Academy. I actually became Foreign Secretary of the Australian Academy of Science in 2014. And that was really sort of important for me because I really care about international science relations between countries and supporting science in my region in Southeast Asia. And of course, I'm still doing lots and lots of mathematics, which is what I absolutely love. So if you look for my picture on Google, you'll get pictures of me giving lectures, which is what most mathematicians do a lot of. They give, there's lots of teaching and lots of lectures. I built up a research group, spent a lot of time writing applications. Fun things are doing research and seeing my students succeed. And here is a graduation photo where that's my husband, John, that's me. He was formerly my PhD student, but we were both supervisors of Hassan. And this Hassan's wife is also a colleague, another mathematician. So did lots and lots of work outside of the university with the academy, with the International Maths Union. I was on the executive for 2 terms as an executive member, probably the first EC member from Australia. And now we've got another person on the IMU executive, Nalini Joshi, who's the first vice president of the IMU from Australia, which is fantastic. Do lots of work with professional societies and with maths education with kids in schools. I'm now patron of the Maths Association of Western Australia. We in the UWA and with the help from all the universities in Western Australia, we set up a junior West Australia Junior Maths Olympiad in the early 90s, and it's still going. And its parent body was the Australian Maths Trust, which has a range of programs running from school maths competitions through to training and selecting of our International Maths Olympiad team. And 3 years ago, we sent our first team, Australian team, to the European Girls Maths Olympiad. I've been chairing the Australian Maths Olympiad Committee for 20 years, and I just thought we can never get enough girls on the team. Why don't girls want to be in the team? Because if they don't see any girls there, they think maybe it's not a place for them. So we tried to get some advice about what to do for girls at this elite level at school. And we were told, we learnt from our colleagues overseas, that maybe the European Girls Maths Olympiad was perhaps the best girls Maths Olympiad internationally. And so we tried to send a team there. And so this is the first team, 2018. And we've been sending the teams each year since then. Of course, this year it had to be a virtual competition. So I don't know, you told me there were going to be lots of perhaps undergraduate women in the audience, and I have no idea if there are any there, but I would like to say, if there are, don't be afraid to follow what you're passionate about. I mean, the world needs lots of bright young people, and that includes men and women. So I really very much wish you all the best, and I'm very happy to answer any questions. Shall I stop sharing this so we can see each other more?
Thanks so much, Cheryl, for sharing your journey with us. So with the Prime Minister's medal, what did that mean to you?
Oh, I found it a really especially heartwarming acknowledgement of mathematics. So there's been the Prime Minister's Prize for Science for 20 years, and it had once been won by an epigeneticist who was a mathematical statistician, but it had never been won by a pure mathematician before. And I was just so pleased that that it could be awarded to a mathematician, pure mathematician. And also there'd been never an award to someone working in my state in Western Australia before. So that was also another special aspect of it. So it was really very special for me.
Right. So maybe if people want to ask you some questions, they can raise their hand, and then I will ask them to unmute and ask their question. Would that be all right,
That's
Cheryl?
what. That's
How much
fine.
longer can you spend with us?
Oh, I'm fine. Yes, my husband's not home yet.
So if any of the audience members wants to ask a question, please use the raise hand button option that you have where the participants list is, and then I'll name you and you can unmute yourself and ask Cheryl a question if you want to do that. I think people are feeling shy.
Oh,
No one's, or they don't know about the raise hand option. Oh, there's Riddhi. Riddhi has raised her hand. Riddhi, go ahead. Please unmute yourself and
Uh, yeah, I want to know, Cheryl. Thank you first of all for such a wonderful talk. It was
oh,
really clear
thank
and
you, Edie.
inspiring for us, and I'm very happy to be in this talk. And I want to know what has changed from the time you were a student in terms of more girls being taking up mathematics and in Australia. That is.
I think there's a lot more girls doing mathematics, and um, and so what has changed also is that there's a lot more um, jobs available for mathematicians or for people with the mathematical training, and everyone knows much more about this. So people in finance industry and IT, I mean, those sorts of jobs didn't even really exist very much. When I was thinking to be to do study in mathematics, this guidance officer also told me there are no jobs in mathematics. That's what he said. He said the only job a mathematician can do is to be an actuary, and Queensland has an actuary, and we only need one. He said. So all of that's absolutely changed. There are so many more opportunities and need for people with strong mathematical skills that there's many more mathematically trained people in the workforce, and I think young students know this. There's also more challenge activities for kids in schools. Like there were not many maths competitions or enrichment classes. I don't recall any maths enrichment opportunities that I had, um, except that there was one competition that the Maths Teachers Association for my state ran, and that's actually what gave me the confidence to do mathematics. I I competed in that competition, and I thought to myself, I didn't tell anybody else. I thought, if something happens, if I do okay, then I will definitely go and try and do mathematics at university. And so I tied for first place. And so that gave me the confidence to say, I'm going to try and do mathematics. So I think that these days there's many enrichment opportunities, there's much more encouragement, much more challenge activities for young people at school and then going through to university. I think it really is different, and I hope it continues to be different. How is
So,
it in India?
in fact, one of our, I mean, we have now a lot of girls doing mathematics, but someone had, Professor Noori had written in the chat saying 90% of the students in his university are girls, or doing maths are girls. So that's
Wow. Oh my goodness.
quite a large number.
Wow. I don't think we're at that level.
so may I ask one more question?
Yes.
What about graduate level and at faculty level? What percentage of are women?
In mathematics faculty, I think it's more, unfortunately, more like 16, 18%. And and then if you look at everybody, all the women and maths in the faculty, they tend to be more at the lower levels. But I think by now there's about 20 women who are professors of mathematics in Australia. So we've only got 40 universities, 40. Yeah, so it's not, I mean, you have many, many, many more universities. Yeah. So we don't have as many staff.
So, but what about PhD students?
Oh, PhD students. I'm not quite sure of the proportion now. There's certainly the proportion goes down as the level goes up, but there's still quite a few girls doing PhDs. Probably amongst I've supervised, 30 students or something, and the majority were men, but there's quite a few girls.
Okay, nice to know.
Okay.
I think Pooja Singla wanted to ask something.
Yes. Cheryl, I read somewhere about your academy for women students. So can you tell us more about that?
Oh, it's just been announced. Yeah, there is a big high school in Perth with very, very enthusiastic maths and science staff, and they would bring their students down to public lectures that we would put on. And I met the students and the teachers at a couple of meetings, and then they started writing to me saying, we want to set up a special enrichment program, especially for girls, and we want to call it the Cheryl Praeger Maths Academy for Girls. Can we do that? And I said, oh, I'd be honored. You know? And with the pandemic, it wasn't possible to go and see them until very recently. So the first week in September, they invited me to a father and daughter evening where I gave a talk, and they asked me to announce that this academy would be set up, and it will start in a few weeks' time for years 7 and 9, and then next year it will have eventually classes in every year level. So I think in schools where there is a wonderful headmistress and wonderful staff, most amazing initiatives can happen, and I think this is one of them.
So what talk did you give to the young children?
Well, they wanted me to talk about how I'd become to be a mathematician. You know, what was my life journey, and then my head of department was there. He was talking about what you could do with mathematics, where mathematicians were needed in the workforce, and then some of our students were there from the Math Union, and they had an activity that was involving the fathers and the daughters, and they were all busily doing mathematics. And at the school, the people that learning hospitality, they had prepared food and drinks and that. So it was everyone through the whole school which was involved. It was a really amazing evening. Actually, they sent me a link to a 3-minute video of the evening. I can send you the link. It's absolutely gorgeous video.
Shobha Bagai has a question to ask about. Shobha, do you want to unmute yourself and ask?
Yeah, Geeta, hi.
Hello.
So hi, good evening, and a nice talk.
Thank you,
So I
Shobha.
wanted to know, even in India, we find that lots of girl students are entering into the maths discipline. But when it comes to higher education, and getting a faculty position and moving from the faculty position into a little bit of an administrative position, that's where we find out, a downfall of the women. So is it similar in Australia too?
Oh, I guess everybody, when they're coping with their work, I suppose it's whether there's a flourishing research culture which engages our colleagues in research as well as teaching and service. So for me, I loved everything, and I do know that some of my colleagues would choose more to focus on teaching, some would choose more to focus on administrative tasks. I don't know what's good or what's bad. I think it's an individual thing. Is it the case that some people might choose this because of very high workload, teaching loads or something? I don't know the
My
situation
question,
which.
sorry, my question was a little different. See, it's not about the choice, but somehow we feel that when it comes to the higher education and when it comes to the administrative post, that's where the women, in fact, uh, they are lesser in number at these higher posts.
Oh,
So sometimes it may
Means,
not be because of the choice, but
you mean
yeah,
posts like dean or
yeah,
vice
leadership position.
president?
I think
Yes,
academic leadership positions is what Shobha is meaning.
yes. I think in Australia, uh, there's a majority of men, but there are quite a number of women vice chancellors. Three vice chancellors. Actually, I wrote to one yesterday. We're writing an article about women in mathematics in Australia for the Association of Women in Maths 50th anniversary thing next year. And
We've done that as well, Cheryl.
you've
We
done
wrote
that? Oh, I'm late. I'm late. But we were wanting to check some things. Yeah, so we do have some women who are at that top level, and Deputy Vice Chancellor. Our DVC research was a woman, a mathematician actually. She retired at the end of last year. And at some stage, I set up the position of Dean of Graduate Studies. It was huge effort, and I had to choose at the end of those 3 years whether I wanted to stay in that role where I would have gone up into higher executive positions or go back to mathematics. And for me, I couldn't see myself not doing mathematics, so I went back.
Shivani Rastogi, do you want to ask a question? Shivani, can you unmute yourself and ask your question?
एक्चुअली मैम मेरी इंग्लिश इतनी अच्छी नहीं है तो
आप हिंदी
आई
में
डोंट
पूछ
नो.
लेना, मैं उनको बोल दूंगी. हिंदी में पूछ लो आप.
ओके ओके मैम, मैं एग्जैक्ट वे में ये पूछना चाहती हूँ कि जैसे हम ग्राफ थ्योरी कर रहे हैं, हमें जैसे कुछ प्रूफ्स ऐसे होते हैं कि हम उनको प्रॉपर डायरेक्शन में नहीं ले पाते हैं, और फिर उसमें ना हमें प्रॉब्लम ये होती है कि हम अपने आप को पीछे कर लेते हैं, और इंटरेस्ट होने के बावजूद भी तो हम कैसे उस चीज को मतलब कंटिन्यू रखें कि हम उसमें अच्छा अचीव करें.
Cheryl, Shivani, I think, is a student who wants to know. I mean, generally, when we are doing pure maths, there's a tendency to sometimes get stuck in proofs and not being able to move forward. And it tends to set you back. So she wants to know, how do you keep yourself alive and make yourself better at understanding these concepts and being able to solve problems?
I guess where I am right now, I have so many problems I want to work on that I don't have the time to do all of them. But when you get stuck, that really is a problem. And if you're a student, I hope that you have a guide, a supervisor, because when there's a really hard problem, an experienced supervisor would be able to say, I think you should try these special cases, or perhaps you can think of going in this new direction. And part of becoming an expert is to have have your supervisor and to learn new tools, new methods. Just try to learn as much as you can. I guess you read things, you listen, and you try special cases. These days, trying special cases will probably mean trying them out computationally, getting some experimental evidence. It's often getting the evidence from computing a lot of small cases with the computer that might suggest something that might be true. And my younger colleagues are much better at that than I am these days. And they will often say, well, maybe this is true. And then sometimes I'll have to say to them, do you know it's true, or do you just think it is because you found some experimental evidence?
The last two questions, I think, or three questions, and then we will finish. The first person, Abhiti, can you ask your question?
Hello, ma'am.
Hello.
I'm an undergraduate student of mathematics in Bangalore, and I study in the Indian Statistical Institute. So I had a general question for you.
Yes.
In my class, a lot of my classmates have already decided which field of mathematics they want to pursue. I mean, generally, as in would they like to go algebra, topology, applied statistics, and so on. But I somehow find that I can't commit to one branch as of now. And I'm in my third year of it's a 3-year undergrad program. I'm in my third year. So I just wanted to ask your opinion. Do you think it's time for me to decide what I should do? Or is it fine if I can just look at everything in breadth, but not in depth?
I think you probably, Aviti, will find something that you are passionate about. I wouldn't worry about it just yet. Somehow I loved everything, and I was sad to stop doing things. So I was sad when I had to stop doing chemistry at the end of first year, and sad when I had to stop doing physics at the end of second year, and sad when I dropped out of some of my applied mathematics courses at the end of third year. So in my fourth year, I still took some quantum mechanics and relativity, along with analysis and algebra and topology. So I still had quite a broad education through to the end of my fourth year. By then, I kind of knew I liked algebra because I had the opportunity of doing a project. So perhaps in your fourth year, will you have an opportunity of doing a maths project with somebody?
My program is a 3-year undergraduate program.
Okay.
But I do plan to do a master's in mathematics. So
yes. So perhaps you'll be able to choose a master's which is kind of broad, but you might discover that you like certain broad areas like pure maths rather than applied, or applied better than statistics or something. And then you can give yourself a broad range of courses to start the master's. And I always tell my students who ask me the same question, you are never going to make the final decision in your life. If you choose to do something and you become very expert in it, but then you decide you'd like to go in a different direction, you can always choose to do and learn something more. You're never going to lose out by one of the experiences, one of the hard works that you've done on one of your projects. Actually, I had a student who came to see me when I was on sabbatical in Oxford, and she'd just been up to Edinburgh, and she was trying to work out what she was going to do for her PhD, and she was so worried. She didn't know that if she chose to do one field for her PhD problem, she might be cutting herself off from something else. And in fact, I said, if that's the nicest thing and you feel drawn to that subject, do it. You can always choose something else later. I don't know if that helps.
It does. Thank you. And if I could just say a little bit more, So when I received the email for this talk, I looked you up, ma'am, and you're such an inspiration. I think I got a little shot of inspiration after looking at your profile and your Wikipedia page, and I finished a bunch of assignments that were due.
Thank you.
So it's an honor to be here. Thank you so much for giving this talk.
Thank you.
Thanks, Abhiti. Mahima wants to ask a question, and after that, Aparna, and then we will have to stop because I think we can go on, but some online things are very tiring. You realize it after the event. So Mahima, can you ask your questions? A question, please. Mahima, are you there, or you want me to ask it? I think she had a question which was to do with when we're looking at atoms of the symmetric group, why are we concentrating on cyclic? I mean, she's written it somewhere. Let me just see if I can find it. So in the study of atoms of symmetry, why do we talk about non-cyclic simple groups? Why not cyclic or finite? Oh, okay, Mahima is here. I'll ask you her.
Hello.
Yes,
It's an honor to ask you a question, Cheryl. My question is, in the study of atoms of symmetry, do we always talk about non-cyclic simple groups of infinite? Why not about cyclic or finite, or why not non-simple?
So the atoms of symmetry are the simple ones. That's because that's what we mean by atoms. Otherwise, we would chop them up into smaller bits. And the simple groups, some of them are cyclic of prime order, and some of them are not cyclic. And the classification told us just what all of them were. So infinitely many of them are these cyclic ones, the C2s and the C3s. But you don't have a choice over what the simple groups are in your group. You might make all these different composition trees, but you always get the same collection of simple groups involved. Some of them might be cyclic ones and some of them might be non-cyclic ones. So if you were going to do the composition tree for the symmetric group, the full symmetric group, you would just get one root and two little shoots coming out of it and two leaves. And one of the leaves would be cyclic of size 2, and the other would be all the rest of the group, the alternating group. So you get a mixture of cyclic and not cyclic.
Aparna, do you want to ask?
Thank you, Cheryl.
Thank you.
Yeah, thank you very much, Geeta. It was a pleasure to be a part of this lecture. It was really interesting, Cheryl. And I want to ask women, it is a very general question. Women usually restrict themselves while managing their family and their job, or while doing research, you restrict yourself. You have responsibilities somewhere else also. So did you ever feel like that, or did you ever feel restricted, or how did you manage the both fronts?
Thank you for that question. It's a very important one.
Yeah, because I think
really,
that is
really
the
important
idea behind women going.
Yeah, I very, very much wanted to have a family and have children, and I really wanted to be a mathematician as well. And they were the two things which were most important to me. So, and then for me to be a mathematician, I really wanted to be very active in research. So that was the most important bit. Somehow I felt that if I took a lot of time off with my children, that I wouldn't be taken seriously as a mathematician. And I hope that that has changed these days, so that there's a better range of choices that women can make. So in fact, I didn't take a lot of time off, but it did mean that I had to choose a lot of other things. Like I used to be able to cook better than I do. I can't cook as well as I used to because I don't have the time. Or we have to get people in to help clean the house because I just don't have the time to do all of those things. So there are a lot of choices in deciding what's how we're going to spend the time. With my children, I had to have them at a childcare centre for much of the time when they were little, and that was another choice instead of staying home with them so much. And I hope that I didn't damage them by not, by having made that sort of choice. But I think every woman has to think what is her passion and what is most important to her, and hope that she has a partner who will support her, because if it's a family, then each partner is responsible for making it all work. I don't know.
Cheryl, there have been lots of very nice comments in the chat box. I hope you'll get a chance to read it, and especially from Professor Ajit Iqbal Singh. She is our a senior colleague and has been a mentor to many of us, and she's one of these people whose enthusiasm for mathematics, like you said, 2020 plus, you're still going strong.
Yes.
She's like that for us, and she's complimented you greatly. I don't know if Professor Ajit Iqbal Singh might want to say a word herself. I don't know whether she's
A wonderful
there.
talk
Yeah.
and wonderful interaction is going on. We are learning a lot in simple ways. You have classified any problem in simpler problems and dealt with each one of them in their own excellent way. I think your dictum is simple. Classify and decompose and deal with each part separately. That is your lesson. And it is not a lesson just to a woman mathematician. It is a lesson to all mathematicians. It is a lesson to all scientists. It is a lesson to all. From my point of view, there is no difference between a man and a woman. Each one of them has the problem and they have to tackle the problem. That is true. And in Delhi, as Geeta already said, we have more women students, but it is a dynamic process, it seems. They have their aims and the aims get modified at each level. And some go into higher things, some go into more practical things, and some go into education, some go into research. But
Yes.
whatever they do, they must do well. Their
Yes.
sincerity of purpose is very important. And I think, research is good, but at the same time, undergraduate research is just as good, but they should do it sincerely and with all their might. And it doesn't matter whether you are left or right, whether you are woman or man, and you have expressed that very beautifully and with your lecture. Another thing that I want to say is that finite groups have many applications in physics, in astronomy, in where everything that you come across, and in quantum information theory. Not only representations, projective representations have great applications in quantum information theory, and I dabble with that a bit. And I'm 76, but I consider myself still as a student, school student, undergraduate student, postgraduate student, and a researcher, and less of a teacher, but more of a student. And that is what helps me. I learn, and I learned a lot from you today, and thank you very much. And Geeta, Gridhi, Neela, everybody for arranging such a beautiful, practical, excellent talk and interaction. Thank you very much.
Thank you, Professor Singh, and thank you for your.
She's also a poet, which she hasn't mentioned. So she writes poetry and very nice
Wow.
poetry. So Cheryl, unfortunately we have to call an end to this wonderful interaction that we've had and a super talk. We've really enjoyed it very, very much. And I have to do a little vote of thanks. So thank you very much, Cheryl. And thanks to the IWM for organizing this talk. And I think the silver lining of the COVID pandemic is that we were able to have you give a talk. The National Board of Higher Mathematics Department of Atomic Energy, Government of India sponsors us. And of course, the Committee of Women in Maths have also been helpful in supporting us in the previous times when we've had foreign visitors visit us in India. You know, they've helped, that money has helped bring women visitors to India. So we're thankful to all of them. And before we end, I want to mention that on 30th of October, we will have the third talk in this series, and we have Terracina, who's going to speak to us on 30th October. So I hope all of you will join us for that. And thank you very much, Cheryl. And lovely seeing you online.
Lovely
Thank
to
you
see
so
you,
much.
Geeta. Thank you. Bye-bye.
Hi, Pooja. Sorry. By the end, my brain was blanking out. Okay.